Get rid of our exceptions for a minute. Let's go ahead and use our abbreviation for mercury. What are we going to write down? Here's mercury, atomic number 80. We're going to write down Xe, and we're going to have to build up after that. So after 54 comes what? 55, and then 56. So this would be filled up. That would be 6s2, and I would write it down. And then after 56 comes 57. What is this right here? It's 5d1. What comes after 57? 58. And what is this now? It's 4f. So we're going to have 4f, 14. And then after 71 comes 72. Well, you only want to count up this electron right here how many times? One time, not two times. So this is 5d1, 5d2, 5d3, 5d4, 5d5, 5d6, 5d7, 5d8, 5d9, 5d10. Here's the electron configuration for mercury. So how do we handle things that are really above atomic number 56? We got to include these electrons down here, right? Because you don't go 57 electrons, 72 electrons. If somebody would have wrote down 6s2, 5d10, then you would have not counted up all these electrons that are actually inside the mercury. So you'd have to have that 4f14 in there. Yeah. Well, we might as well do that. Let's say we were looking at something like uranium. It's atomic number 92. The previous noble gas would be Rn, which is radon. And then we would build up from there. After 86 comes 87. So we'd say 7s2. And then we'd say 6d1. And then we'd say 5f1, 5f2, 5f3. Now, look, because this is a Chemistry 1 class, I do want you guys to realize this. The periodic table is wonderful for giving you the correct predictions for most of the elements. You start to get into some of the heavier elements down here. Then you start to get more exceptions, but I'm not going to hold you guys responsible for some of those guys on the test. Really, what we're worried about is the ones that we've gone over, which is going to take, which is going to go ahead and help you do the vast majority of these things correctly. But you got to realize that you got to include your F's when you do your D's. But you guys should be able to do electron configurations now for quite a few of these things. All right, let's do this. Let's look at something called an electron dot diagram. And what an electron dot diagram does is it shows the number of valence electrons for an atom. So if we look at something like, we'll take an example of some of our guys that we've done. If I look at fluorine, it was 1s2, 2s2, 2p5 was the electron configuration. What's the highest energy level? N equals 2 is the highest energy level. And then how many electrons would be there? 7. There's 2 here, plus 5 here is 7. So what we do is we write down the element, its symbol, fluorine, and then we're going to write down dots to represent electrons. So how many dots are we going to put around our fluorine here?
7.
7. We're putting the 2 from the S and the 5 that are represented in the P. So the two S's actually go together. So you put the two s electrons together, and then the electrons in the p orbitals, they actually will be in different orbital. Let me rephrase it. They'll be in different axes. They're only going to double up when they're forced to. So this would be, let's say, an electron in the p orbital that's on the x-axis. This might be the one that's on the py, and this one might be the one on the pz. We talked about the three different axes that the p orbital has. And then that gives you those. Well, now you're forced to put those guys together. So this would be the electron dot diagram for fluorine right here. Now, this would also be acceptable. And you have to realize that all it's doing is if I write this down on my hand, okay, and I do this, it's still the same structure. It's just, I'm just turning it, okay? I could take this and do this with it as well. I could do this. Notice that now I'm showing that dot what? That electron. It's pointing up. So this is an okay answer. This is an okay answer. Or even if you put this down, that's okay too. It's just how you're turning the atom, how you orient it. What would not be okay for an answer? Let's see, 3, 4, 5, 6. That would not be okay. Because you're not going to have these 3 electrons all inside one orbital. Each orbital can only hold 2 electrons at maximum, not 3. We actually wrote that down in the notes. Plus, you've got this empty space. Wouldn't these two push it to where there's the empty space? That's why that would not be correct. Okay. If we look at chlorine, chlorine would be 1s2, 2s2, 2p5, I'm sorry, 2p6, 3s2, 3p5. What's the highest energy level? N equals 3. How many electrons in it? 2 plus 5 is 7. So 1, 2, 3, 4, 5, 6, 7. Notice that the electron dot diagram for chlorine is the exact same thing as with fluorine. Now, based off of that, if I asked all of you to do the electron dot diagram for bromine, would you guys write out an electron configuration to determine it? I would say no. And in fact, all these guys are going to have how many electrons for the dot diagram? 7. 7 for all of these. Well, notice that this did not happen by chance. Look at what group number it's in. The new system says it's in group 17. That's the new naming system we use. The old system was 7b. Notice 7b, it's got what? 7 valence electrons. What Roman numeral is this for? 6. Take a wild guess. How many dots for their dot diagram? 6. All these guys are 6. Matter of fact, if you wanted to see that, oxygen would be 1s2, 2s2, and then it would be 2p4. Highest energy level is N equals 2. 2 plus 4 is 6. So I'd go 1, 2, put the s's together. Then you put the p's in separate sides. Now, there's 4 of them for these p orbitals, yes? So now they're going to have to double up in one of the rooms. So that would be acceptable. What else would be acceptable? That right there would be acceptable. Okay. What would not be acceptable for the dot diagram? That, because oxygen doesn't have 8 valence electrons. This would not be acceptable. Because again, you put the electrons in separate orbitals until they're forced to go ahead and start doubling up. So that would be wrong. So without doing an electron configuration, Aaron, tell me how many electrons for gallium's dot diagram? 3 would be correct. Tell me how many dots for this one? 2. How many for this one, Austin? 1. Jacob, how many for this? Okay, so let's say we're not sure. So we're looking at scandium. Scandium is, if we looked at it, would be argon, and then it would be 4s2, 3d1. Do you see that? Yes? Here's my argon, 4s2, 3d1. By the way, notice with the D, don't you always subtract 1 from the row number? Will the D actually ever be in the outermost energy level? The D sublevel? No. 5s2, 4d. 4d is a lower energy level than 5s. The D will never be in the outermost energy level. What's interesting, in order to get to 4f, let's see number 58 here, didn't you have to go through 6s2? Will 4f and 5f ever be in the outermost energy level? No. This is the reason the outermost energy level can only hold how many electrons at maximum? 8. Because the outermost energy level is always going to be made out of just the S sublevel and the P sublevel. Any questions with that? So, what's this guy going to have, this guy going to have, this guy going to have, this guy going to have for their number of dots? They're going to have 2. So scandium would have 2 valence electrons and 2 dots in the dot diagram. Now, let's make a really easy generalization. Since these guys are going to be 4s2 and then they're going to be 3d something, all these elements in the D bracket, the intertransition metals, they're all going to have how many dots for the dot diagram? 2. Except for what? Chromium, palladium, and tungsten, and copper, silver, and gold. These 2 columns, how many dots do they have? Well, this is why we went ahead and wrote them down for our exceptions. Remember that chromium was argon, and then it was 4s1, 3d5. Remember, the D is never going to show up in the highest energy level. So chromium is going to have 1 valence electron. There's its dot diagram. So 1 dot, 1 dot, 1 dot. Remember, what was the copper? The copper was 4s1, 3d10. So 1 dot, 1 dot, 1 dot. So what we can do is we can basically, for electron dot diagrams, we can just count. It's 1, 2 dots, 2 dots, 3, 4, 5, 6, 7. These guys are 8. He's an exception. He's got 2. And then just realize that when I said the 2 for my intertransition metals, that this column and this column are actually 1 dot. How do we feel about that? By the way, if somebody said, what about these lanthanides and actinides, these metals down here? Remember that F is not going to be in the highest energy level. And what did you have to do to get down here? You had to go through 6s2 and 7s2. So these are going to have, unless they're exceptions, they're going to have a tendency to have 2 dots when you do the electron dot diagram. Now you're going to say, well, what's the purpose of doing a dot diagram? A chemist does not say to themselves, well, I'm going to go ahead and write down a dot diagram of carbon today. That's my job today. That's what I want to look at. We learn about electron dot diagrams so that we can understand chemical bonding and chemical reactions, and that's what's really important. We want to understand chemical bonding because, for example, what happens if I want to look at a material and I want it to be really strong, I want it to be made out of really strong chemical bonds, then I want to look at things like the strength of the bond, the number of bonds, and electron dot diagrams help do that. So this stuff is really practical, although we're not really doing that today. Okay, you might as well hit stop.